Okay, so I'm going to go through sections 14.6 and 14.7 with you guys, just to make sure that we're clear on what information is being presented in these two sections. Okay, 14.6 starts off with a little bit of a recap. It says, so far you've investigated whether the force of friction depends on the kind of surface and the contact area between the two objects. So let's just recap real quick what we did learn here. This is actually from lab 14.5. What we learned was that the surface area has absolutely nothing to do with how much friction an object is going to encounter. So if you guys think back to, let's see if there's a picture of the block. Yeah, if we look at this block from 14.5, whether it's this side or this side that we are pulling with the spring scale, the surface area does not affect the force of friction at all. So it seems like it would. Like logically you'd think, well, if there's more surface area in contact, you're going to have to apply more force, but that's not the case. So that's an important one to keep in mind. Surface area has nothing to do with the amount of friction. Now, what we also found was that surface type does have something to do with the amount of friction. So if we compare this side that's covered to the side you can't see under here, that's uncovered, we should find that this surface requires more force, which means there's more friction with this kind of surface than with the smooth surface. So if we go back to 14.6 real quick, the recap is that the kind of surface or surface type does affect friction. However, the contact area, which we call surface area, does not affect friction. So this section goes on to say, well, what about the weight? Does the weight of an object affect the friction for the same surfaces? So if we're going to look at these two blocks, let's look down here. These two blocks, clearly this one's larger than this one. So this one has a greater mass, but we're going to keep the surface type constant. So it's that same smooth surface that we're going to use in this particular experiment, which they're going to talk through here. So it says, to study this, we investigated the frictional force on two blocks of different weights, a short lighter block and a long heavier block. Their weights were 1.3 newtons and 5.05 newtons. Using the same procedures that we used in the preceding experiment, we found that the least force needed to move the lighter block was 0.5 newtons, and for the heavier block was 2 newtons. So clearly the friction was greater for the heavier block than the lighter one. So as you can see, before we even go any further, weight certainly does affect the force of friction. The heavier block experiences more friction, the lighter block experiences less friction. So then they go on and they say, okay, then we placed various weights on the lighter block and measured the force of friction for each combination. By the way, you'll see some pictures like this when we go over the chapter 14 test, so kind of understanding this is important. It says the results are shown in table 14.2. The data was then graphed. Within the range of the data, the force of friction is proportional to the weight. So let's take a look. Here's the graph. So what they did was they took that little block and they just added weight to it. So we have 1 newton of weight, 2 newtons, 3, 4, 5, 6, and 7 newtons. So we continued to add weight to it and then measured how much friction there was between the block with the weights on it and then the table. And so the force of friction is basically how much force do we need to apply to get it to move, and that's exactly equal to how much friction there is between the two surfaces. So you can clearly see from the graph that as you increase the weight, the force of friction also goes up. And it is a proportionality. The two characteristics of a proportionality are that it starts at the origin and it has a constant rate of change. So it's linear, a straight line whose slope we could calculate. So this is a proportional relationship, friction versus weight. Now, this is the part where it does get a little teeny bit confusing. Okay, so we graph it. The force of friction is proportional to weight. The proportionality constant is called the coefficient of friction, and it will be different for each pair of surfaces. So let's look at this formula really quick. If we want to figure out the force of friction between two objects, we can look at the weight of the object multiplied by the coefficient of friction. So let's look at the graph for a second. Anytime there's a proportionality like this, we can figure out what the constant relationship is, and then we use that constant in the formula to calculate the relationship between these two variables. So we can calculate the slope of the line, which is the constant rate of change, which would be the constant in the formula. So if we're looking at how the force of friction and weight are related to each other, we can look at the slope of the line. Okay. Now here's the thing about the coefficient of friction. It's going to be specific to the two types of surfaces that we're dealing with in a particular scenario. So for example, if I had a block covered in sandpaper and I was going to try to pull it against a table covered with sandpaper, two sandpaper surfaces trying to move against each other would clearly have a lot of friction. So there's going to be a lot of friction to overcome to get that object to move if we set it up that way. So that coefficient of friction is going to be pretty high. It's going to take a lot more to get it to move because of the surface types involved. Now, if on the flip side I took a block like this and I covered, let's say, what kind of surface could we use? Let's just say it's ice. Let's say it's a block of ice. And I'm going to move it against a table that's made of ice. Two very sleek surfaces that don't have a lot of friction at all. Those two surfaces would very, very easily move against each other with very, very, very little friction. So the coefficient of friction in that scenario would be very small. So the coefficient of friction is basically shows you the relationship between the two surfaces involved. So this will be specific to the two surfaces. So if we're looking at the force of friction between two objects, the weight of the object that's being pulled multiplied by some constant that reflects the two surface types involved. So that's what the coefficient of friction is. This accounts for surface type. So if we go back for a minute and think about what we know about the force of friction, we know that surface type affects the force of friction, and we know that weight affects the force of friction. We know that surface area has absolutely no impact on the force of friction. So if we're going to take those two factors into account, the weight will affect the force of friction, and then we account for surface type with this coefficient of friction, which again will be specific to the two surfaces involved. Now, when I was going over this with my students, the thing that they found to be confusing, so we've got this thing called the coefficient of friction, and that comes into play when we're talking about the force of friction. When I was reviewing this chapter with my kids, I noticed that if we go back over here to, let's find it here, when we talk about weight. If you go back to the beginning of this chapter and we look here at how weight and mass were related to each other, and they discussed this whole proportionality constant. The proportionality constant here in this formula is not the same thing as this coefficient of friction. And I found my students being confused about this. They saw coefficient of friction and they automatically thought, oh, that's 9.8. No, it's not 9.8. The coefficient of friction takes into account the surface types, and it will be specific to the surfaces that are involved. In order to calculate the coefficient of friction, you would need to have a graph like this that shows the force of friction and the weight, and then you could do force of friction divided by total weight, and then you could calculate what the coefficient of friction is. Again, that's going to be different for every pair of surfaces that we're discussing. Okay? Over here with the proportionality constant, when we're talking about weight, the proportionality constant between weight and mass is always 9.8 on Earth. Okay, because this takes into account how the Earth pulls on a mass. Okay, the pull being the force, right? Weight is the force due to gravity. So here's the mass of the object is a factor, and then how does the Earth pull on the object? That's basically what this proportionality constant is. So if we went to the moon, this proportionality constant would be very different because the moon does not have nearly as much gravity. So this proportionality constant would be less because there's less pull on objects on the moon because there's less gravity. So this proportionality constant in this formula is 9.8 when you're on Earth. And then anywhere else you might happen to travel in the universe, would have a different proportionality constant depending on its gravity. Okay, most of the time we're going to use 9.8 because most of the time we're talking about weight on Earth. Okay, but just keep in mind, if you go to the moon, or you go to Jupiter, or you go to Mars, any other planet would have a different proportionality constant due to its particular gravity. And keep in mind, this is not the same as the coefficient of friction. Okay, so I wanted to draw your attention to that because I noticed with my students that was definitely a point of confusion. Okay, let's see. It's also important to keep in mind, because my students often ask me, well, how do you know this? One of two ways. If you're given a test question about this particular formula and this particular relationship, you will either be given the coefficient of friction, or you will be given the force of friction and weight, and then you can calculate the coefficient of friction. And again, if you're not sure how to do that by looking at the graph, think about how you would do it in algebra. If you want to solve for this, you can call this x, and then you would just, if these two are known, you would divide both sides by weight, and you could solve for x. So force of friction divided by weight would also help you figure this out. So it would either be given to you in a question, or you can calculate it based on knowing the weight and the force of friction, and or calculate the slope of a line if it's given to you on a graph like that. So that is basically 14.6. All right, here's the last section of chapter 14, Newton's third law. And if you read this in class today like you were supposed to, there was probably a little bit of confusion, which is part of the reason I'm recording this for you guys. Keep in mind the way that these IPS books, chapters, sections are written. Oftentimes what they're trying to do is to prove to you why something is what it is. So they start at the beginning and they walk you through a piece at a time, trying to prove to you the concept in that section. So in this section, we're trying to prove Newton's third law, okay? So sometimes I think what's better, or at least a little bit easier, is if we kind of go to the end first and start with the end, and then going back, it kind of makes a little bit more sense. Now that you've already read this section today, I don't mind going to the end and starting there. So let's look at what Newton's third law says, and then I'm going to give it to you in my own wording. It says, in fact, so here's where they actually wrap up the whole section, all the stuff they're trying to prove to you. In fact, all forces known today that act between two objects along the line that connects them are equal in strength and opposite in direction. This property of forces is known as Newton's third law. Okay, Newton's third law is also sometimes referred to in a couple of different ways. Sometimes we look at, you may have heard it's stated such as, for every action there is an equal and opposite reaction. You may have heard it referred to as force pairs, where every force has a force pair that goes with it, that forces always act in pairs. So I oftentimes try to go back to those two ideas to help make sense of this particular law. Let's look at how it's written in the book though for a second, so we can try to make some sense of it. Okay, so let's move this up a little bit. Okay, so let's start at the beginning. All forces known today that act between two objects. So the first part that it's very important to keep in mind is that we're talking about two objects that are in contact with each other. Okay, so that's what we mean when this is what they mean when they say all forces known today that act between two objects along the line that connects them. Because that's the part where people are like, what are you talking about along the line that connects them? We're just talking about two objects that are in contact with each other. So if I have a tabletop and I have a block sitting on the tabletop, the block is in contact with the tabletop. Two objects, so block, table. Two objects in contact with each other, okay? Then it goes on to say, are equal in strength and opposite in direction. So if this block has a weight of 2 newtons, okay, so the block would be exerting a force of 2 newtons onto the table. Newton's third law tells us that the table then must be exerting a force of 2 newtons back onto the block. So equal in strength, 2 newtons and 2 newtons, opposite in direction. So the block is applying a force down and the table is applying a force up. Okay, so keep in mind the block applies a force to the table applies a force back to the block. Equal in strength, opposite in direction. And this is the law, the rule, for every 2 objects that are in contact with each other. Now, it's very easy to see how this would apply between a table and a block, but what sometimes gets people thinking that maybe, how could this possibly be true, is if we're talking about something like a car crash, in which they talk about at the end here. So it says Newton's third law may seem strange to you. Is it possible that when a heavy truck collides with a small car, the forces acting between them are equal and opposite? And this is where you go, wait a second. If there's a huge big old truck and it runs into a teeny weeny little itty bitty car, how is it possible that the force the truck applies to the car is equal to the force that the car applies to the truck? It kind of doesn't make sense. So let's keep going. It says, keep in mind that equal forces does not mean that the effect of those forces are equal. Okay, so let's think about it this way. Let me turn this over. I can't draw at all, so I'm going to say small car, big car, because that's about as good as it's going to get with me. If they collide, the small car will apply a force to the big car, and the big car will apply a force back. Keep in mind, it's when they touch each other. The forces don't act over a distance like this, okay? So it's when they come in contact. So if this little itty bitty car is driving in this direction and this big old car is driving in this direction, the moment that they touch each other, that they come in contact, remember, Newton's third law is about contact forces, forces that are in contact with each other. So let's say the little itty bitty car applies 50 newtons of force to the large car. The large car applies 50 newtons of force back to the small car. Okay, that still seems a little bit strange, but let's make some sense of all this in terms of the effect. Okay, at the moment they touch, Newton's third law tells us equal forces in opposite directions, and that's just the law of nature. It works. That's how it works. We can't really violate laws of nature because we have found so far that they always hold true. So the little bitty car applies a force to the big car applies a force back to the little bitty car. Now let's look at effect. The effect of that force. Okay, Newton's third law does not say the effects will be the same. So let's say this little tiny car has a mass of 10 kilograms, okay, and the big, huge, gigantic car has a mass of 100 kilograms. Okay, so let's look at the effect of those forces. Here's what you haven't learned yet, Newton's second law. Newton's second law says that force is equal to mass times acceleration. Okay, so let's say if the forces are equal, let's say so for car number 1, the little bitty car, it's going to look like this. Force, so 50 newtons, is equal to 10 kilograms times acceleration. Now let's think about acceleration as the effect. Okay, so effect we'll be able to see the effect in the acceleration of the vehicle after the force is applied. Okay, so if I do it like this, and then I say, well, I want to solve and see what the acceleration is going to be, I can divide both sides by 10. Okay, so let's find my calculator because I get very nervous about doing very simple math in my head when I'm being held accountable for it on a video. So just to ensure that I don't embarrass myself, I'm going to actually do the math. Okay, so 50 newtons divided by 10 kilograms would result in an acceleration of 5 meters per second squared. Don't worry about the unit for now. We'll just look at the number numerically. So this would be the effect, okay? That would be the effect on a little car. It would accelerate at a rate of 5 meters per second after this big car applied 50 newtons of force to it. Now let's look at the big car and see how that would play out. So we would have 50 newtons of force, right, because the forces are equal to each other, just opposite in direction, equal to 100 kilograms times the acceleration. So again, the acceleration is going to be the outcome, the effect of this force on that big car. So again, we could divide by 100 on both sides, and we would find that the acceleration would be 50 divided by 100 will be 0.5 meters per second squared. Okay, so now let's go back and see how this plays out. These two cars collide with each other. As they collide, as they come in contact with each other, the little car applies 50 newtons of force to the big car applies 50 newtons of force back to the little car. Here's the effect. The little car will accelerate at 5 meters per second squared. Okay, so big car hitting little car means the little car is either going to get crunched up and or tossed aside, moved in some direction at a rate of 5 meters per second squared. The big car is barely going to feel that. Half a meter per second squared. So maybe there'll be a little dent. Maybe the effect will be a little dent in the car, or maybe it'll, just scooch over on the road a little bit, but it won't be nearly the effect that same force would be on the smaller vehicle. So the reason I wanted to explain that to you is so that you can see and buy into a little bit more how Newton's third law actually works. Yes, when they come in contact, the forces are equal in opposite direction. Absolutely, no doubt about it. The effect, however, will be very different depending on the two objects that are involved. Now, if the objects are identical, then it'll probably be an identical effect. But if there's a big difference in the sizes of the objects, then the effect will be very different depending on how big each object is. So that's the gist of Newton's third law. Let's give a couple of examples, and then I'll go back to some of the reading sections real quick. If I'm sitting on a chair, I apply a certain force to the chair. The chair applies that same amount of force back to me. And the reason I know it does is because if it was not applying the same amount of force back to me, then the chair would not hold me up and I would fall to the ground. And that would be super embarrassing. When I'm walking, I'm applying a force to the ground. The ground is applying a force back to me. That's equal in strength. If it didn't work that way, then the floor wouldn't be able to hold me, right? If it didn't apply the exact same amount of force back to me. What else? There's every example of a force that exists has a force pair. So if you can identify a force going in one direction, then you can also identify its force pair that goes with it, the opposite force going, or the same force going in the opposite direction. And that's where for every action, there's an equal and opposite reaction. The only thing I don't like about that particular phrasing is that it implies that they don't happen simultaneously. Action and reaction imply that the action comes first and then later on at some point the reaction occurs, and that's not the case. If you look at this example here with the two vehicles, those forces occur simultaneously at the exact same moment. So as long as if you like the phraseology of action-reaction, then you can use that, but please keep in mind that they occur simultaneously. Action and reaction do not mean that they happen at different times. It's always simultaneous. Equal in strength, opposite in direction at the same time. If you kick a soccer ball, for example, I apply a force to the ball applies a force back to my foot. The reason I know that is because if I've ever kicked a soccer ball with no shoe on, I can feel the effect of that force of the ball applying that force back to me because it stings a little bit. When you hit a baseball, you apply a force to the bat applies a force to the ball. The ball also applies a force back to the bat, which sometimes makes the bat break. If you've ever watched professional baseball before, you've seen that. So for every force that exists, there is a force pair that goes with it. Equal in strength, opposite in direction. Now, just to clarify a little bit of what's going on here with the reading, what they're doing here from the beginning is trying to build up to Newton's third law to prove to you why it is what it is. So what they do is they take, let's see, I'm going to start kind of down here. So here's what they say. They take a block, which you're familiar with now, and they put it on this cart. This cart has what they call basically frictionless wheels. And the reason they have to do that is because anytime two objects are in contact, there's going to be friction between them. And what we're trying to focus on is the block and the cart. We don't want to focus so much on the cart and the table. So if they put what we call frictionless wheels, then that takes that friction out of the equation. And so now we can really just focus on these two particular objects. Okay, so here, let's pick up where it says here. So if we now pull on the block, so if we take this spring scale, hook it to the block and pull in this direction, if this spring scale wasn't here and you pull on the block this way, the whole thing is going to move this way. So then we go, okay, to keep the cart at rest, then I can put a spring scale, hook it up to the cart, and pull in the opposite direction. And if I apply the same amounts of force in opposite directions, then this whole thing will remain still. Okay, and that's where they get A equals D. So if this is force A and this is force D, if this whole thing is not moving, that means these two forces must be equal to each other. So if I pull this way with 4 newtons and I pull that way with 4 newtons, this will stay at rest because the forces are balanced, right? 4 this way and 4 that way makes this thing stay still. It's kind of like tug of war. If both teams are pulling with the same amount of force in opposite directions, no one's going anywhere. It's going to stay still. So now we start off with this. Okay, so these two are equal in force. Great. Now let's concentrate on the forces acting on the cart. So here we have, so here's what they say. Let's see. Okay, so let's look up here. So if we have, the spring pulls the cart to the left with force A, okay? The force of friction exerted by the block pulls the cart to the right with force B. So now what we're looking at is just the forces acting on just the cart itself. Okay, so we're pulling on the cart with A, and the block, because of the friction between the two objects, is pulling on the cart in this direction. Remember, friction always opposes motion, no matter what. That's what friction does. Sometimes it's good, sometimes it's bad, but it is what it is. So if we're pulling this way on the cart, and we're pulling this way on the block is applying friction to the cart in the same amount that's being pulled this way. And we know that they're the same amount because nothing's moving, right? If nothing's moving, everything's at rest, forces are balanced. So the force being applied to the cart this way by the spring scale and the force being applied to the cart this way due to friction, those are equal. Great, now let's look at just the block. So if I'm pulling on the block with a force of D going in this direction, and the block doesn't go anywhere, that means the force of friction between the cart and the block, this frictional force between them, this must be equal to D as well. Again, because the block is not moving. So just the forces acting on the block, right? This force here is acting on the cart. So the forces acting on the block are me with the spring scale pulling this way, and then just the natural friction between objects that are in contact with each other. So those must be equal because, again, the block's not moving. So same rationale here. A and B are the two forces acting on just the cart by itself. D and C, or C and D I should say, are the two forces acting on just the block. Okay, great. Now, they go all the way down here and we go, okay, if A is equal to B, oh, do they do B? Because they're going to do that later. Okay, if A is equal to B and C is equal to D, oh yeah, and don't forget, all the way back here, we said A and D are equal to each other, right? A is equal to D because the whole thing is not moving. So if A is equal to B, and C is equal to D, and D is equal to A, there's this thing called transitivity, right? Where it's basically called, like in my mind, connect the dots. If this is equal to this, and this is equal to this, and this is equal to this, then this must be equal to this, right? So here's how it goes. A and B are equal, A and D are equal, D and C are equal. And you can go back and look at each of the diagrams. And I already explained those 3 scenarios and why those are equal, those equalities exist. So if you look at all of that, then B equal to A, equal to D, equal to C, B must be equal to C, right? So let's look at B and C again. B is the force of friction on the cart, C is the force of friction on the block. Now we're talking about two forces equal in strength and opposite in direction, which again, if we go back and think about why are they telling us all this information, why are they walking us through this whole thing, the whole point is to build up to Newton's third law, which says two objects in contact with each other, equal forces in opposite directions. So the force that the block is applying to the cart is the same as the same force that the cart is applying back to the block, which is what we just talked about, right? When I went to the end and started there. Okay, so this is their way, the author's way of proving to you why Newton's third law is actually true. And they sort of give you the data and kind of walk you through it. So it says, in other words, the strength of the frictional force exerted by the block on the cart equals the strength of the frictional force exerted by the cart on the block, right? Block and cart. They each apply the same amount of force to each other, just in opposite directions. These two forces act, of course, in opposite directions. Okay. Don't worry so much about that next paragraph and this next paragraph as well, because it all just builds up to here, Newton's third law. The reason I focused a lot on the cart and the block is because there's a couple of questions on the chapter 14 test. When you see it, hopefully this explanation will serve to help you understand those questions that you'll see. So that is Newton's third law, and I hope that helps. If there are any questions on either of these sections, please send me a message on Edmodo or feel free to